Hello, good morning. Sorry to abruptly turn off the music there. I hope everyone's having a good day. Um, I think this is going to be a good week. Last week was pretty hard. It was a short section, but a rough one. Um, and it was very cold. And I think it's going to be better weather this week. And the sections that we're doing are a little less theoretical. Um, so I think we're going to be in a good place. Let's start just by saying hi to each other. So could you please turn on your mics and your cameras and wave hi to everybody? Hi. Say hi. Hi.
Hi.
Hey guys.
Hello.
Hi. Um, so you'll need to have your cameras on just for a minute while we say hi. Today, the question I have for you is I would like you to share your thoughts about snow. Um, Someone asked me in direct message what song was playing. It's the first New Order song from their first album by New Order. I gave up on finding music without words because it's too hard. So now I just have music whose words you can't really distinguish while they're being played. So that's what our new genre. Anyway, tell me in the chat what you think about snow. The purpose of these questions in the chat is to make sure everyone has their chat open so that it's easy for you to ask a question during class. So you can press return whenever you like. What are your snow thoughts? Please share them with us in the chat. Thoughts about snow. And again, this will make you open your chat and type something. You have any opinions you like about snow. Yeah, I pretty much agree with all of these thoughts about snow. Yeah, it's great. Again, but yeah, it's been kind of a lot. I grew up in Connecticut and then I lived in Chicago. I have had enough snow. I don't need any more anymore. I'm good. Yeah. So hopefully we're done with that soon. Okay. So good morning, everybody. You shouldn't need your cameras again until the end of class, although I will really appreciate if you ask me questions in the chat or just interrupt with your voice at any moment, because I am losing my mind just talking to the computer screen in my house. So I appreciate your questions. Here's what we're going to do today. We're going to do a quick actually, I'm going to tell you about the reflection, but you're going to do it later. We'll have a lot of time to carefully go through what's in the reading in Kickoff this week, all the material that you're going to need to know for the homework. We'll finish by doing some limit problems together and talking about Piazza, and that'll be the day. Okay. So first of all, our schedule, very much a normal schedule for the week. The only weird thing in the list is this algebra boot camp, which is going to be due in week 7. So you have this week and next week to work on that assignment. Still, it's a little long. So you probably, if you haven't started it yet, you might want to start doing it. It is optional though. You could also just ignore it and that would be fine. So you get some engagement points if you do it, but you don't have to do it. Okay, this says do this in Canvas right now, but please don't do it now. You can do it later. So if you go to Canvas and into the Monday reflection, you can do this assignment until midnight tonight. This is an article that I contributed to a book, and then it was published in a magazine in pink for some reason, and that's what you have a link to here. And this book was like, prominent people in the math community, like, you know, president of the American Mathematical Society and stuff like that, talking about how they themselves had struggles in mathematics throughout their education and career, just because struggle is really part of being a mathematician. And so I shared this very short article about basically how I'm a dumbass and everything is hard and that's fine. So excuse my language, but that's what it is about. Let's see. There is a direct message here to me, but I will address it. Someone is asking why the points of the homework didn't add to 50. Yeah, you can only get like a 98.2 or something on your homework, or a 99.2. One of the problems had an error in it that I found last semester, and asked WebAssign to remove this part that I didn't think made sense. But then I guess the points didn't get recalibrated. So problem's just missing points. So I'm sorry that it didn't equal 50. It should be really close. It should be like 48.8 or something like that. Anyway, I'm sorry about that. So anyway, this assignment in Canvas, you can do this anytime before midnight tonight. It's about hitting the wall and having math be something that's difficult instead of something that is easy. Anyway, you can do that later. Because I want to talk about the material from the book because there's a lot of stuff going on and I want to make sure everybody's in a good place to start their homework right away. So the first thing is this definition of continuity right here. I cannot stress enough how important this thing in the green box is. That's only true if the function is continuous. That is the definition of what it means to be continuous. And what it says is that the limit is equal to the value. The limit of the function as x goes to a point is equal to the value of that function at the point. Now, clearly that's not always true. There are plenty of cases where the limit and the value are different. Some of them are pictured below. If they were always the same, then we wouldn't ever talk about limits. We would just do the values. Wait, I have another message. Oh, yeah, the answer is yes. Somebody asked if on Friday we can go over previous week's homework too. And yes, of course you can do that. Yeah, go ahead and ask me questions in the chat. It's just fine. Okay, so but if the limit was always equal to the value, then we wouldn't even do limits, right? We would just plug stuff in. But when a function is nice enough, so this is when a function is nice at a point, then the limit is equal to the value. Now, in high school, you probably heard that a function is continuous if you can draw it without picking up your pencil. That is almost true. It's almost always true. There's some fine points that we'll get to in a few slides, okay? But if you think about it, what you're saying when you say you can draw it without picking up your pencil is that where you're headed with your pencil is where you're going to end up. And that happens at every point. You never start going somewhere and then magically materialize somewhere else. Where you're headed, the limit is equal to the value. Notice that things can be continuous just on one side. The left limit equals the value, or on the other side, the right limit equals the value. And also notice that there's this definition of what it means to be continuous on an interval. To be continuous on an interval, you're continuous on the inside. And if you have closed dots, you're continuous including going up to those values. And we'll talk about that more in a minute when we see some theorems. But like, for example, this function right here, at this point that I put the green arrow on in the first picture, the function is continuous there. The value of the function is 1 and the limit of the function is 1. And that's in fact true at every single point. At every single point, if I plugged in the value and then got the height for the function, I would get the same thing as if I were approaching from the left and the right, okay? But in this one, the second one, something bad happens right here. What's happening here is that the limit as x goes to 1 from the left of the function and the limit as x goes to 1 from the right of the function are not equal. So from the left, what is the limit? As I approach from this side, what are the heights approaching? What are the heights? You can say it out loud or you can type it in the chat. As I approach from the left, maybe I said right out loud, maybe that's the confusion. As I approach from the left, what are the heights of this function approaching? Here's the heights. 1, thank you. Yeah, 1. So only 2 people alive. So we get 1. From the right, the heights are approaching 2. In fact, they're constantly 2. And so when you put these two together, what happens is that the limit as x goes to 1 of the function doesn't exist. But f of 1 is what? Is 2. This is all for this example right here. So from the left and the right, the limits don't agree, which means the limit doesn't exist, but the value is 2. So this function is not continuous at 1. It is not nice. Okay, so sometimes the limit doesn't exist and the value does, sometimes the opposite, sometimes they both exist, but they're not equal to each other. That's what happens in the third picture. All of those things are bad things that could happen to you. All of those things are bad things that could happen to you. And if the limit and the value are the same, the function is nice. And if the function is not nice, then the limit and the value will not be the same. In fact, it's our definition of nice. Continuous is nice. Okay, so, oh, I'm sorry. If you wanted to take a picture of that for some reason, please go ahead because I'm about to erase it. Okay, so, okay, so we just basically saw there's different types of discontinuity. Sometimes the limit or the value exists or doesn't exist, or they both exist, but they're not equal. And these pictures here are talking about that. So like, for example, here, both of them exist, but they're not equal. That's happening here. Here, both of the limits from the left and the right aren't equal. That's what we saw on the previous page. That means that the limit doesn't exist. It can't possibly equal the value. And this third one, the limit is infinite, so it can't possibly equal the value. So this is like a little bad. This is more bad. And this one here is so bad. Okay. And by bad, I mean like kind of how repairable it is. Like the removable one, the first one, I could just take this point and stick it in this dot and it would repair the function. I mean, we can't because this is the function, but that's like how far away the function is from being nice. It's just 1 point away from being nice. But the second picture, you would actually have to shift a whole part of the graph down to the other. That's like more broken. And this third one is like super broken because there's an asymptote at 2. I mean, literally, I could even put a value in here. It doesn't matter because the limit is going off to infinity. That is not going to equal any number, no matter how high I make it. It's really bad. It's just not repairable. You'd have to basically take away the asymptote to fix it. A lot of the problems in your homework from section, whatever the first section is, 1.4, are going to be like, can you tell from the graph what kind of limit it is? And then what kind of discontinuity is? And also, can you describe it in limits? Okay, so notice that the part that's not in the blue box, these terms, removable, jump, infinite, and the pictures, you may have seen that already and be able to associate the words to those pictures, but you need to go a step further and also be able to describe these pictures in limits in the blue box. That's the part that might be new to you if you've seen limits before. So we're describing this concept of continuity, and in particular, how continuity fails by explaining what's happening to the limits. Now, if you have any questions, I'm happy to hear them now, or you can put them in the chat before I erase this round of scribbles. Okay, just go ahead and keep asking things. I'll answer when I can if it's in the chat. Okay, but there is a kind of abstract part to section 1.4. It's these theorems. There's some theorems here with actual names that like every math person would know. The extreme value theorem and the intermediate value theorem are our first two named important theorems. Later in the semester, we're going to have Rolle's theorem and the mean value theorem, and then finally the fundamental theorem of calculus. So we have 5 named theorems in this course, and 2 of them are in this section. Both of these theorems basically just tell you that when your function is nice, that nice things happen to you. And both of them, as we're going to discuss them in the middle and in a minute and unpack what they mean, both of them are obvious once you understand what they're saying, but very difficult to prove, and in fact, beyond the scope of this class to prove. It requires something called it requires the least upper bound axiom, which is something we're not going to discuss. And so it's a very obvious result, you'll see. But actually proving that it has to happen is very difficult, and we're not going to do that. Okay. But it is important that you understand these theorems and then this happens. Both of these theorems start by assuming that a function is continuous on a closed interval. Okay. So what that means is basically you've got a function and an a and a b, like with thumbtacks at a and b, and then though that's the value of the function at a and at b, and then it's connected by a string. Okay. And the string definitely starts at the first thumbtack and goes in an unbroken way to the next thumbtack. This is the equivalent of drawing it without picking up your pencil. Okay. So continuous on a closed interval is super nice because it means there's two dots connected by a curve, an unbroken curve. Super nice. And the first theorem says that whenever that happens, you can find a value where the function is the highest and a value where the function is the lowest. There might actually be more than one place where the string goes as high as it can, if it goes up and down, or maybe it goes up and stays there like a plateau. But there's at least one place where the string is at its highest point, and there's at least one place where the string is at its lowest point. So those places are the x values, capital M and capital N. Capital M and lowercase m. And if you look at the statement of the theorem, look what it's saying. There exists m and n. There's our quantified statement. We can find m and n such that f of m is the maximum and f of little m is the minimum on that interval. Okay, that's what this is saying. This only happens if the function is nice. So this, if f is really nice, continuous on a closed interval. Everywhere inside is continuous, and also leading up to the endpoints, if you look at those little arrows, it's continuous from the right to A and from the left to B, connected. We don't care what happens outside that, but it definitely connects up. Okay, so both of these theorems start by saying if f is really nice. The second theorem, the intermediate value theorem, says that all intermediate values are taken on by the function. So that if we started at A and ended at B, then every single height in between happens for the function. So here in this picture, you see the C right here. That is the corresponds to this height of K. I realize I just crossed out the graph a lot, but the point is that every height between f of A and f of B, the function goes through that height somewhere. So the K is like the height. Notice here it says for every K between f of A and f of B, that's my intermediate value between f of A and f of B. There exists some C that maps up to that height. That's what the intermediate value theorem says. Again, it's kind of obvious. Both of these, like if your string connects two thumbtacks, your string has to go through every height between the two thumbtacks to get from the first one to the second one. I mean, that's how string works, right? And that's how nice functions work. So again, it's an obvious conclusion, but it turns out to allow us to say a lot of things later on that are important. And in fact, our other named theorems are going to depend on these two theorems. Okay, so in particular, there's this one at the bottom here. This theorem is actually useful. So sometimes a theorem just tells you that a nice property happens. That's what the first two are doing. But this next one is actually useful. It's basically the k equals 0 case of the intermediate value theorem. So if you take the intermediate value theorem and you have a point above the x-axis and a point below, and you choose your height k to be 0, the x-axis, it's saying that your function has to pass through the x-axis if the function is continuous. And what that means is that your function can only change from positive to negative if it either goes through the x-axis or has a discontinuity or a place that is not defined, okay? And I want to show you why that's useful. We use it all the time. In fact, we used it extensively in chapter 0. So I'm about to erase this in case you're taking notes by screenshot, take it now. And I'm going to show you why this last theorem, the intermediate value theorem when k equals 0, is actually useful. By the way, there's a lot of conceptual questions about these on your homework. And when you do the reading, definitely slow down around these pages here, because everything I explained about these theorems is done out like in careful detail in the ebook. You can read about these theorems, and that's what's going to help you answer the questions about those theorems in the book. Okay, so let's see why this is useful. If you remember, sometimes we want to solve a problem, like we want to know where a certain function is positive. Okay, so let's say we wanted to know where this function is positive. We would make a number line and we would mark on it all of the zeros of our factored function. And then we would test one point in between, like for example, between 0 and 3 is x equals 1. And if I plug x equals 1 into this thing here, I get positive, negative, negative. I'm just plugging into the 3 factors. I get x is 1, x is minus, and then when x is 1, I get -2. And then when x is 1, I get -3. So I get positive, minus, minus, which is positive. In this interval here, I could type in maybe x equals 3.5 and get plus, minus, plus, which is negative. In here, I could plug in maybe x equals 100 and get plus, plus, plus. So that's positive. And then over here at x equals minus 100, I get minus, minus, minus for the factors. And then if you read off the number line, the solution set is x living in 0 to 3 union 4 to infinity. And that would be the answer. So we've done this a number of times, and we're going to in chapter 0, and we're going to do it again all the way to the end of the semester. We'll be doing this with something called derivatives. So, but we used the intermediate value theorem here, and here's where we used it. When we said that at x equals 1, we had positive, we then concluded that the function had to be positive in this whole interval. Now, why did we do that? We did that because the function is 0 at x equals 0, and the function is 0 at x equals 3, and the function is not 0 in between 0 and 3. And the function is very nice and continuous. This is a beautiful function. It's just a polynomial. Those are all continuous. And so there's no way, if the function is ever above the x-axis between 0 and 3, there's no way that it can get below, because it would either have to jump over the x-axis or there'd have to be another root, and we know there aren't any roots. So we actually are using the intermediate value theorem all the time when we do a problem like this. So I wanted to it's a very theoretical thing to talk about, but I also wanted you to understand that everything that we do has a reason why it works, and the theorems are those reasons. Okay, so sometimes we gloss over them or we can't prove them or whatever, but like everything, we're not just calculating stuff. There's some theory under here that's allowing these calculations to work, and that's like the real beauty of what's happening is hiding in that theory, right? When we do this stuff that I wrote all over the screen here, that's us being a calculator, right? Wolfram Alpha can do that. Desmos could graph this function and you could get this solution. Symbolab or whatever other thing that people use can solve stuff like this, right? But the real interesting part is, why does this process work and what's underneath it, and what theorems are sort of driving all of this math. So that's not practical. If you're a practical person, that perhaps is irritating to you. If you're a theoretical person, that's the interesting bit. Anyway, so that's an example of how we use the intermediate value theorem. I actually want to go to something more practical now. If you want to take a picture of this, just so you have one more example of solving an inequality, this is a good time. And I'm going to go ahead to something a little more practical, which is limit rule. So we're now in section 1.5. In section 1.5, we're going to learn how to calculate basic limits. And basically, we're going to lean pretty hard on continuity, because if a function is continuous, then the limit and the value are the same. Okay, so this first thing is saying that these very basic types of functions are continuous. I mean, linear functions are just lines. Those are definitely continuous. And then down here, power functions, those are also continuous. So because these things are continuous, that means we can do all of these limits by plugging in. Whenever we see a linear function, we can just plug in to find the limit. So I realize I crossed out a lot of the words there, but let me just show you an example. Like limit as x goes to 2 of 3x plus 1. This is linear. He is our friend. That is a continuous function. They're everywhere that we look, the limit and the value will be the same, which means that we can plug in to find the limit is 7. Okay, now that is f of 2. Okay, so notice here, we're just plug in x equals 2. And we get the limit. Now this isn't always going to work. It's only going to work for super nice limits. Okay, but linear functions are nice. Power functions are nice. Even a function like, and here's where I said that your drawing with the pencil thing is a little bit of a lie, like f of x equals 1 over x. We can't draw this function without picking up our pencil. It is not continuous for all real numbers, but this function is not actually defined for all real numbers. It's defined from minus infinity to 0, open, and then it's also defined from 0 to infinity, and it is continuous on both of those pieces. So everywhere that we would plug in to do a limit, if nothing bad happens, that'll be our answer. So it's not a lie that being able to draw it without picking up your pencil means it's continuous. I just want to stress that like there's different ways to be continuous. And I would say that this red function here, 1 over x, is continuous on minus infinity to 0, and also on the open interval from 0 to infinity, but it is not continuous at 0, and it's not continuous from minus infinity to infinity. Okay, so it gets better though, because not only can we do those limits by plugging in, we can do any combination of these types of functions by plugging in. So I'm just going to pick the sum rule here to look at. Look at what this is saying. It says, well, why can't I point at the actual thing? Let me see. I don't know why I'm so bad at pointing today. Let me do that again. I got excited, I guess. So let's look at that thing. What it's saying is that the limit of a sum is equal to the sum of limits. It says if we want to take the limit of something that's added up, we can take the limits of each piece and then add up those limits. So here's an example. I could do the limit as x goes to 2 of x plus x squared. Now I know from the previous page that this is a linear function and I can find its limits by plugging in because it's a continuous function. And this is a nice power function. I know those are continuous, so I can do their limits by plugging in. And the sum rule right here says that I actually can split these up and consider them separately. I can do the limit of x and I can do the limit of x squared separately. And because both of those pieces are continuous, I get 2 plus 2 squared, or 6, as my answer. So now we can compute limits of any combination of power functions and linear functions, sums, quotients, even compositions with one inside the other. This is basically all algebraic functions. So anything you can write down with powers and roots and sums and quotients, and then those things nested, all of those things, if we plug in the value to the limit and nothing bad happens, then that's the answer. Okay, so when things are good, they're very, very good. So this theorem, if I had to give it a title, I would call it Everything Works Great. Everything works great for limits. Everything you would want to have happen happens. You can do the limit even of a quotient by taking the quotient of limits. It's fantastic. Okay. Now, everything works great when things are continuous or combinations of continuous functions. So I will put a little warning asterisk here, and the asterisk is for combinations of continuous functions, because you're about to see that red on the balloons gets me every time. It's a really stark warning. You're about to see that things can also get very, very bad. Okay. Everything simple works great. That's what I'll call this one. Okay. So how do we use this? Well, this theorem here on the top is kind of like a summary of what I just said. Oh, I effectively crossed it out by doing that. Let me be a little less emphatic. Okay, this one up here that I circled is basically a summary of what I just said. If your function is algebraic, it's just built out of powers and combinations and things like that. And if C is in the domain, all we have to do is plug it in. All we have to do is plug it in and we get the limit. Now, again, I want to stress to you, the limit and the value in general are not always equal, because if they were, why would we even talk about limits? We already have values, right? But if your function is very nice, algebraic functions are nice, and they're continuous on their domains, then everywhere we can calculate the limit by calculating the value, okay? Now, here is sort of the beginning of a warning. A dark cloud is forming, which is that bad things can happen to you. And one of the bad things that could happen is that you get a 0/0 limit. And that is happening right here. When I plug in 1 to this, I get 1 squared minus 1 over 1 minus 1, which goes to 0/0, which is, wow, that's a very angry, I didn't mean to make the face so angry. There, now it's kind of a worried face. That makes us worried. Okay, 0/0 is a ridiculous face. Is very bad, and we don't know what it is. But sometimes you can just cancel out that badness. So in this particular example, if you factor the top, you get these two pieces here, and notice one of the pieces matches the piece on the bottom, and so I can cancel those out. So I had, like, here's my original limit, and here is a simpler limit. And the simpler limit is easy to calculate. We just plug in and nothing bad happens, and that's the answer. So if I covered up the original limit and only had this part here at the end, that's an easy problem. And the cancellation theorem says that the answer to the easy problem is actually the same as the answer to the hard problem. The value of the function that's being computed isn't the same, but the limit of those two functions is the same. In fact, the function that this is it's the function that looks like x plus 1, but with a hole at 1. That should be a hole there. I can't draw in white, so I can't make a hole, but let's just pretend there's a hole there. That's what our original function is that we were taking the limit of. And notice the limit, oh, well, don't do that. And notice the limit is just fine. It's just a value that's messed up, and we tried to compute the limit with the value. Once we cancel, the hole is gone, and we can use the value to calculate the limit. That's basically what's happening. So this red cloud is the first nasty thing that can happen to you. And in section 1.5, I believe it's the only nasty thing that happens in the limit is that you might have to cancel first. In section 1.6, yeah, that's next week. Can we just wait till next week to talk about all the many bad things that could happen to a limit next week? This week, this red cloud will be the only bad thing that happens. Okay, so I think I'm about to do a bunch of examples like this on the next slide, but would anyone like to interrupt me with a question first? I will wait. Okay, well, let's go on and take a look. So I've got all these questions. I actually have 2 pages of this. See, so there's a lot to talk about here. I would like you to tell me in the chat the following. Some of these limits are easy to calculate because when we plug in where x is going and look at the value, nothing bad happens. And since everything here is a nice continuous functions on their domains, that'll be the answer. But some of these, when we plug in, a bad thing happens. And specifically, you get divide by 0. And in fact, worse, you get 0 over 0, and you're going to have to cancel. Let's find the good ones first. So for example, I'll do the first one here. If I plugged in x equals 0, I would just get 0 squared minus 1, which is negative 1. That's an answer. Nothing bad happened. So therefore, that's the answer to the limit. If a continuous function, you just do the limit by finding the value unless you're at a bad place. We weren't in a bad place. So here's my question. In the chat, could you please type to me the numbers of other problems that you think we could do just by plugging in and no bad thing would happen? We could just plug in and we get a number, and so that's the answer to the limit. Which ones are like that? You can just type it in the chat, or you can even say it out loud. $31. Oh, wait. Well, 31 is actually where something bad. I think you might be answering the opposite question, because 31, something bad is going to happen. When I type in 1, when I plug in 1, I don't know why that was so shaky. That was weird. When I type in 1 for x, I'm going to get 0 over 0, and that's bad. I'm going to need to cancel. So that was a bad one. And a good one, let's see, 29. Yes, for 29, when I plug in 2, I'm nervous about that denominator, but the denominator is just 4, and there's nothing wrong with 4 as a denominator. What else is good? Good ones. Let's see. Someone privately said, oh, 29. Oh, that's the one I just did. 26. Yeah, I see that too. 26 is good. If I plug in, I just get a number, and that's fine. What else we got? While you're thinking about that, by the way, this is just a bunch of problems from the ebook. Your web assign is taken from these problems, but this might be a good week to do some extra problems to make sure you can do everything. And this is how I would suggest looking at the problems, like look through them and find ones that you think are fine. So is anybody else alive out there that can type in here and tell me which ones, when I plug in a number, nothing bad is going to happen? Someone guesses 28. I agree. There's a bunch of crappy decimals in there, but there's nothing like really bad that's going to happen. 37, I agree. 37, there's a denominator, but nothing bad is happening. 33, 33, something bad is going to happen, because clearly the top is 3, right? Is 0. That's bad. But the bottom becomes, let's see, 3 times 9 is 27, minus 24, minus 3. So it's actually 0 over 0 for 33. So that person that suggested it said 33 question mark, because the top was clearly 0. But if you plug it in, the bottom is bad too. So both 33 and 34 are bad. 32, I agree, 32 is fine. 31 is not fine because you get 0 over 0, but in 32, you get negative 1 over negative 1. There's no problem there. Nobody said 30, but 30 is, oh, because it's bad. 30, something bad will happen to you. 27 looks nasty, but there's nothing bad that happens. There's no 0 in the denominator. 35 and 36, they look a little crazy, but weirdly, they're both just fine, right? They look bad, but at both of those points, everything's defined and it's fine. And in fact, even 38, just plug in 4. That's going to be your answer. So in this slate of problems here, there's only 4 that require any work. And remember what the work is going to be. The work is going to be that you do algebra to simplify and factor. So you're going to do algebra, and specifically, you're going to simplify factor, and cancel. Tons of examples like that in the reading. You can look, we did one earlier in this section. All that happens is that no other bad things are happening. Again, next week, many more bad things will happen. And in fact, later on in the class, more and more bad things will happen, especially as we go into 232 and get to different types of functions that aren't these nice ones anymore, like trig functions, exponential functions, log functions. That's all for 232. Speaking of which, if you go to YouTube and you Google videos about solving limits, there's going to be way more complicated techniques and functions than what you need to know right now. Because again, we're not doing those complicated trig and log functions right now. And also, we're only doing the very basic types of bad things that could happen to you. Later, you're going to learn something called L'Hopital's rule, which you will love and want to use it for everything, but we don't know it yet. We're not even anywhere close to knowing it because you need to know derivatives, which we also don't know. So don't just go YouTube stuff all over the place. Look at the videos in the resources because they're in exactly the same spot as you are right now. Okay, let's look at the next page. So the next page, here's some more. Now, bad stuff is happening all over the place on this page. Like this one's bad. This is bad. 42 is bad. 43 is bad. 44 is bad. This is bad. This is bad. All of these are bad. I think this one's probably going to work out okay. And this one looks okay. So you can see as the limit gets more interesting, it's great that we can solve a basic limit by plugging in the value. That's those blue ones. But all the ones of interest are starting to be red. And each of these, again, you're going to need to use algebra, simplify, factor. The ones that are in the red box are all kind of a certain form. They're all difference quotients. We'll see this more in the next chapter. These are specifically limits you're going to need to know how to do next chapter, which is why they're here. Anyway, you'll see lots of these calculations in your WebAssign. I wanted to talk before we finish. I wanted to slow down and take a few minutes to talk about Piazza, but I'm sorry. Did somebody want to ask me about this before I go on to that? Because I want to talk more about procedure than math for a minute. Okay. Okay, fine. So, there we go. Okay, so Piazza. Piazza is where my office hours are 24 hours a day, 7 days a week. This is where you should be asking math questions to me, okay? Look at this response time. I have a very fast response time. I will get back to you quickly about your question, even if it's late at night or early in the morning, or I'm just somewhere on my phone. If you've given me the tools I need to answer your question, I will answer it very quickly, okay? I mean, sometimes it's not 9 minutes. Sometimes I'm busy doing something and it might take a couple hours for me to get there, but then we can have a back and forth. And it's also all public, so everybody can benefit from that. I know a lot of you have been looking at Piazza, but not posting to Piazza. And I wanted to just give you a quick encouragement to post on Piazza and to talk about how to effectively post to Piazza. So first of all, it can be anonymous. When you post, you can choose whether or not everybody can see your name. I will always see your name, but then everyone else will see you as like anonymous poet or something. And so it's totally anonymous. You don't have to worry that someone's going to think you're dumb for asking. I am sure that you've appreciated every question you've read on Piazza. That's how people will feel about your question when you ask it on Piazza. A few quick things. Notice that there's a format for answering a question, which is that you say what homework it is and then which question on the homework it is. You can also ask a question about the reading or conceptual stuff or whatever. And like see someone asked about their total score in homework 5 here, for example. But if it's a question from the homework, you should use this format. And then if you have a question that's also about question 24, for example, even if it's a different question that you're asking about problem 24, you should put it in that post as a follow-up discussion. That means that every question will be in exactly one post and no more. Please do not post multiple questions to the same post, because then I have to split them up into different questions. And please don't repost something new about question 24 if there already exists a question about question 24. Instead, put your question in there, okay? So all of these things are listed in the how to post a question post, which is up at the top. But I do want to talk about one more thing in here, which is being specific. I get a lot of questions in Piazza that say, how do you do number 25? Or I don't even know where to start with number 15. Or, and this is more common, I'll get this. I have done the reading and I went to class and I watched a bunch of videos and I even did the practice another problem, but I still can't do number 5. Can you please help? And I want you to think just for a minute about what would happen if you called, say, your car mechanic with a question like that. And you said, hey, my friendly car mechanic, my car is not working. I read the manual. I opened the hood and looked at stuff. I even had my neighbor come and look at it. I've been working on it all week and my car still does not work. Can you please tell me over the phone what's wrong with my car? Well, no, they cannot, because you haven't said anything about the situation. So I know that I think people are replacing talking about how much work they've done with what actually is happening. Okay. I totally trust that you all have done a ton of work thinking about the problem before you even post it there, because that's why you're there. Piazza, you're like, I've done everything and I still don't get it. I'm going to ask a question. So you don't have to prove to me that you have been working on it. But what you have to tell me is where you're stuck. Like, I did this one. When I look at practice another, I don't even understand what this theorem they're referring to is about. Or I worked on this one and my answer is 5. And here's a picture of my work. And I got 5, as you can see. And where did I go wrong, right? Now I can then look at that and say, oh, you lost a minus sign, or oh, this is how this theorem fits in. And ask and answer your question. Okay, so please be as specific as you possibly can, even if you're completely confused about the problem. Try to figure out what you're confused about. And then the second thing I wanted to point out is that an absolutely excellent conversation happened on Piazza over the weekend. And that was that a person came and started asking questions about the true-false problems. Now, I want you to think about this for a second. If you're doing the web assign and you write true, and then you write false, and then you hit submit and it tells you it's wrong, you know the answer now, right? You know the answer is true. And it would be really easy just to flip it to true and be done with that problem and move on. But this person didn't do that. This person said, I don't understand why it's true and I better figure it out. And so they wrote a post here where they explained why they picked the wrong answer and asked why it was wrong and how the correct answer could possibly be correct. And we had a really nice back and forth conversation. And what impressed me about it is that that didn't have to happen, because they could have just flipped the answer. So quickly, the reason I point this out is if you've been getting really high homework scores, but really low quiz scores, it may be that you're just getting through the homework, but you're not developing an understanding when you go through the homework. You're going for that score, you know? But what this person did, made sure they had the understanding. And so I'm sure that that was reflected in their quiz score later on, because now they can handle questions like that. Piazza is your place to figure out how you understand the homework, and I encourage you to go there. Okay, I'm done trying to encourage you to go to Piazza. I think we're about out of time, so I want to say bye. So if you could just turn your cameras on and say goodbye to everyone. Wish everyone luck out loud, please, for the week. Goodbye. Have a great week. See you Wednesday.
Bye.
Bye, guys.
Bye. Good luck. Stick around if you have questions.